So both virus and worm, being the malicious software, they do some damage. Let's ask the question: what exactly they can, what kind of the damage they can do onto the system. So first thing is they can send copies of itself to the other applications and other computers. So that is the first thing both of them can do. And second thing is they can take some actions without user knowledge. So sitting in the background, silently deleting a file is an action. Or it could be generating some network traffic without the user's knowledge. Usually when does the network traffic generate? Let's say I open a browser and type, let's say google.com or any other website name. That time when I click on the button, then I'm accessing some content. That time the network traffic should originate from my computer to the server, and then from server to my computer. But the malicious software, if it is sitting, the virus and worm is sitting in my computer, although I may not be browsing anything, I am not doing anything, even then in the background it can generate some traffic. That is the an action which is not user behavior driven. So this is not under the control of the user. So normally a type of attacks called as the denial of service attacks or distributed denial of service attacks. These are also called sometimes flooding attacks. We will discuss them in the next few minutes. So such attacks are generated by these malicious software. And the other things that they can do is they can silently harvest the password. So just the example that I gave, the spywares and key loggers actually take the monitor your keystrokes and then collect the password. Those are the another action the malware can take. Encrypt the files and data and delete the data. So these things they can do. So without going into the details of how the malware can harvest the passwords and encrypt the files and delete the files, let's take one particular example, which in this case is the how the malware can actually generate the denial of service attacks and distributed denial of service attacks. We will see that in little more detail. So here is the an example of a denial of service attack. Denial of service attack is that attack which actually targets the availability of the service. Remember, if you recollect the previous class discussion, the security itself is defined under three terms. One is the confidentiality, integrity, and the availability. And this attack, denial of service and distributed and denial of service attack, target the availability of the service. So what kind of the action can take? So I have a server here, which I have named it as the victim server, and on the left hand side there are a bunch of systems. So on each of these systems, think of these are full computers. A malware cop is sitting. So a malware is sitting. These are all infected, possibly infected machines. So a malware is here, and this computer, everywhere a malware. A bunch of, let's say, n of them, n such computers are there, and they can collectively do something to the victim. So what they can do? They can send a large set of the packets to the server. So usually the servers got a limited bandwidth. Bandwidth may be, let's say, 1 Gbps, 2 Gbps, whatever the connectivity bandwidth available at the server. If the all these systems collectively generate traffic which exceeds the capacity, the bandwidth available at the server, then that can cause the damage to the server. So any legitimate user who is here, if he is actually trying to access, maybe let's say web server is there, this victim server is having some web application. So any genuine user comes up and then he try to access that web server, they may not be able to. So why they may not be able to do so? Because these programs sitting on all these computers are generating so much of traffic that exceeds the capacity of the link that is attached to this victim server. So such attacks are called distributed denial of service attacks. So the malware, the worm that is sitting inside those computers is doing nothing more without the user knowledge, probably under someone else's control, is just generating the packet, nothing more than that. Send packet to this particular computer, this particular server, maybe let's say some web server, maybe IRCTC web server, with railway ticketing booking web server. To that server, it is continuously all of them together at the same time sending the traffic. So IRCTC web server is having some limited bandwidth processing capacity. As long as if that capacity, either the bandwidth or the processing capacity is exceeded, then any legitimacy, or if tomorrow I go and then when this attack is going on, if I am trying to access the web server and then trying to book a ticket, I may not be able to do so. So such attacks called as distributed denial of service attacks. So this malicious software can actually do such kind of the actions. So one of the special type of the this kind of flooding attack, which was discovered in the day, something called as the SYN Flood Attack. So what this SYN Flood attack does is it abuses the TCP's three-way handshake communication behavior and then generate the attack. So let me write what exactly do. So if you recollect your networking, if let's say I have a client and server, let me denote with letter C and S. C is the client and S is the server. Client is the one usually just request for connection. So a SYN packet goes from the client to the server, and then the server sends a packet which is the SYN plus acknowledgement, and the third one from the client to the server is the acknowledgement. So this is called three-way handshake, a SYN plus acknowledgement, and then the third acknowledgement. So this three-way handshake, the TCP three-way handshake is looking like this. So something interesting happens every time this SYN plus SYN ACK plus ACK is exchanged between the client and the server, particularly at this point of time when the first SYN packet comes from the client to the server need to know packet came from which client, particularly the IP address and the port number, source port number, and from which the client raised the request. All those details are stored in a data structure called as the transmission control block. In short, this is also called as the TCB. TCB stands for transmission control block, and this transmission control block occupies some memory. So every time a connection request comes, one TCP is created. So the amount of the memory taken varies on different system. At the minimum, maybe from 250 bytes to some up to 1000 bytes of the data is consumed for storing this TCP. So what I mean to say is, every time a SYN packet comes from the client to the server reserves some to at the minimum 250 bytes or up to the 1000 bytes of the data for storing the details of that connection. So from this computer using this IP address, this port number at the time, so the connection request came, and this is the sequence number, initial sequence number also goes with that SYN packet. So all these details are stored in this TCP. Is this SYN Flood attack actually abuses the behavior of this one. So particularly it's actually want to consume the memory available at the server and then create the damage. So what the SYN Flood attack does is, the three-way handshake, I still have the client C, and here is an attacker, the client it be an attacker, and then the server is there. Client sends one SYN packet, and then the server sends back hypothetically to the same client SYN and acknowledgement. but the third acknowledgement was supposed to go from the client to the server or the attacker to the server is not sent. So this one, the third one, is not going. And instead of that, what the client does is he sends another SYN packet to the server, and the server again thinks that this is another request using first time it is using a port number, let's say some hypothetical port number, 2300 port number. You made a request, now you use another port number, maybe 2301, and then the server sends another SYN plus acknowledgement packet back to you, and a TCP is created at this point of time. Because this is appearing to be a new connection, a TCP is created at this point of time, and if I continue to do so, another SYN packet and then another TCP and so forth. So at one point will come where the server memory is filled with only these TCPs. There is no more memory left on the server. That time what will happen? The server may not be able to process or create more number of the TCPs and then store or serve the request. So that time what the server typically does is it actually does not take the new request, new SYN packet that are coming are not honored. It does not reply to those packets. So by doing so, if the attacker himself create, let's say the server has got some capacity to create 1000 TCPs, and if the client machine itself is able to create 1000 TCPs, and then the 1001th request coming from probably from a legitimate user is not honored by the server. So in that case, the 1001th request coming from a legitimate user is his connection is because refused by the server. There is a denial of service going on. So that is what attack is. The point I am trying to say is the malicious software, the worm or the virus sitting on your computer can generate kind of the attacks. So unlike the previous attack that I showed on the computer, you may not be requiring large set of the computers to generate the attack, because I know only 1000 TCPs can be created. So as long as I am able to generate 1000 different legitimate looking connections and don't complete the three-way handshake, the memory is exhausted and then the server is actually not able to take new request or process the new request. That is the mess. So the worm sitting in the computer can, or the malicious software degenerate can sit and do such kind of attack. So in this case, you don't require the bunch of system together. Something called as the reflection and amplification based DDoS attacks. So what this in this case happens is the malicious programs sitting on these computers don't send the traffic directly to the victim, which was there in the previous case, but to an intermediate server, and they get reflected back to the victim client. So the malicious computer one sends the packet to this server. Usually there are a bunch of applications, particularly the DNS and NTP are known to such are the usual the targets. So such servers are used as an intermediary or stepping stone to generate the attack. So you send the packet to this intermediate server and they get reflected and come to the get accumulated at the endpoint. In the process, what will happen is these replies that are going from this intermediate server to that computer will be magnified. So in a sense, when this computer one sent the request, it might send, let's say, 100 bytes of the data, and something happens in this intermediate node where the reflector and the reply is quite large, and that reply may be 1000 bytes. The original program sent 100 bytes. Here the reply become 1000 bytes. 1000 bytes, instead of going to the sender, but it is going to the victim. Why did this happen? The sender can spoof the identity of the victim. So the IP address of the victim is used and a packet is sent to the intermediate server, and then because the server, the DNS server or the NTP server, the intermediate server does not know, so it is actually the IP address is spoofed. It genuinely sends one reply, and because the IP address of the server is used, the reply is going back to the server. So now by doing this, what will happen is the first of all, there are not one program is generating the one software is doing the attack, a bunch of them collectively. And second thing is, in the process they are actually hiding the identity by spoofing the IP address. So who actually did the, as if the victim himself sent the request to the intermediate server, the reply is going back to them, but actually they are coming from these malicious software on the left hand side. And the second thing is, in the process they are actually getting magnified. Instead of 100 bytes going directly from the bot 1 to the victim, now bot 1 is sending only 100 bytes, but the at the end when they are received, the victim is receiving the 1000 bytes. So these applications are commonly DNS and NTP. This is called amplification. The reflection is going from one computer and then coming from one computer going to another computer, and amplification is, in the process the data gets magnified. Instead of 100 bytes, now the 1000 bytes are going. That's amplification. So if you imply this, there are two things the attacker can achieve. One is, the amount of the bandwidth required by each of these individual computers is also going to be small, and thereby they become stealth. So I don't have to, first of all, if let's say 1 Gbps is the total bandwidth required at the victim side. So 1 Gbps divided by let's say 1000 bots are there. 1 Gbps, all these 1000 bots together need to generate 1 Gbps, more than 1 Gbps of the data. So now by doing this, I know that it's magnified by 10 times. Each request that I send is, each quantum, the data that I send is magnified by 10 times. I need to send 10 times lesser data from each of these computers. So that is the simple trick. So by doing that, so the bandwidth consumption at the source itself becomes small. Thereby you avoid the detection. So although the programs are, the malware sitting on those computers are sending the data, but they are sending at a very small rate, so that the detection becomes quite typical task. This is one variant of those DDoS attacks that the malware can actually do. So remember, in the previous slide we saw that not one computer is generating the total traffic, but a bunch of them. Now the question is, how these bunch of computers are coming together, how all of them are coordinated and they generate the traffic either directly or through an intermediate server simultaneously. So the synchronization, some sort of synchronization is required. How this is actually synchronized? So that is done with an organization structure called as the botnet. Remember, we did use the name bot here. So bot is a name for malicious software. So how exactly the coordination is done? So that is what we will try to understand here. So botnet has got two terms in it. One is the bot. Bot means anything that is automated. Robot is actually a device which is actually doing some kind of automated task. You tell what it is supposed to do, it is actually do that. So bot is actually that program. Anything that is automated, which is actually doing the task automatically, is called as a bot. So bot itself is not a bad thing to have. So it can do some useful stuff. Anything that you want to do repeatedly, you can assign that to bot and it can do that for you. But if you use that to do the illegitimate things, malicious things, that becomes a harmful activity. So that is what we are interested in. So remember, the previous case, the DDoS attacks and denial of service attack that the bots were generating are a harmful thing. They were targeting a particular server and taking it down. So net is a collection. So if I have a lot of bots and all of them come together and then they execute some activity. Here in this case, generating the traffic is the activity, that's a malicious activity. A network of such systems coordinated and then doing the activity is called as the botnet. So you have a collection of the systems and all of them are doing. So they are probably under the control of one master application which can tell each of these malicious software sitting in different computers to do the certain action at starting at some particular point of time. Usually these botnets are also done for some monetary benefits. Maybe these botnets by taking down this server or by stealing some data, I might get some incentive. That's the goal of the attacker. If they want to do that, then they actually control that all those softwares and then. So usually the companies like advertisement companies, they want to push a particular kind of the advertisements and then they can use such botnets to propagate their own content, or if you want to take down just like in the DDoS case, you can actually do that. Spam mail, sending these spam emails, sitting all of these programs are in different computers, sending the spam emails to a particular target set of people or group of people. So that is another. It is not one computer is actually doing the generating the spam email, but a collection of them together. Because if one computer starts sending thousands or lakhs of emails, then that is noticeable. Instead of that, if you employ a bunch of them, then the detection becomes quite easy. So this botnet requires some kind of the coordination between them. There is a master, there are a large number of the slave programs, and then at what point of time, what action they should do, when they should sit silently. These instructions need to be told to those slave programs. So typically this is done through something called as the command and control infrastructure. Command and control infrastructure is when you instruct, the command is the instruction that is given to those slave programs, and to push those instructions you need to have a kind of the background connectivity. This is also sometimes called as a overlay structure. They are not the slave programs, the malware sitting on one computer to another computer. These two computers are not physically connected. They are located in different places. Maybe one computer here in one place, maybe Mumbai, second computer might be in some other country, in some other state. So all of them need to coordinate because they are all infected. They are under the control of master. So they build a kind of the infrastructure to do this coordination, that command and control structure. This command and control infrastructure are of two types. One is called a centralized command and control, where a centralized server sitting is actually doing the or taking actions or giving instruction to all of these save programs. That uses the client server model because there is a server involved. And second model is called distributed. This is also called as sometimes peer-to-peer botnet. You don't have a centralized server which is actually doing or sending the instruction to all the slave programs, but somebody, the bot master injects some kind of the instruction into one of the program and they actually propagate the I know who is my peer, and then I send the instruction, pass on that information to my peer, and then he himself again pass on that information to his peers, and this like this the information propagates. That is called as the peer-to-peer structure. So the command and control infrastructure is maintained either in a centralized fashion or in this distributed fashion. We will see the diagrams for both of them in the next slide. So this structure, either even if it is centralized or distributed, doesn't matter. You need to have a kind of the stable connectivity. So a lot of times what will happen is, if let's say I have 1000 slave program or computers, and which are infected, malware is sitting in them, and then one of the computer might shut down, and then it might reboot. Then you need to identify which system is actually shutting down, which system is actually up and joining the network. So you need some kind of the maintenance activity that is required. So that need to be robust enough. Who is actually is going on? If let's say my machine is infected, and if I erase all the content and I reinstall the operating system afresh, then the malware sitting on my computer might also go. So in that case, you have one less number of the computer to contribute to the. So the master program which is sitting, which actually gives the instruction, need to know who is actually alive at this point of time, who is actually moving out of the network. And then the changes, whatever is happening, so the reaction time, the moment the instruction is given, and then the action starts, maybe the DDoS attack itself starts, the traffic generation starts, the when that instruction is given, when that activity actually starts, this is called the reaction time, and the time should be minimal. So if you are able to maintain all these things, so I am able to identify the churn, who is leaving the network, who is presently up and running, and the connectivity itself, and then the if the bot is structure has got the small reaction time, then it can quickly get started, and then start generating the traffic. So in order to maintain this structure and then do the MS, the bot actually uses a communication protocol. Usually this communication protocol are of the two types. One is called the IRC, Internet Relay Chat. This is actually a chatting application. So the master and the slave can communicate within this protocol, and the latest variants can also use the web communication or the HTTP protocol as a means to communicate between from either from the bot master to the slave, or between the one malware to the one bot to the another bot. So they use either of these two communication protocols. So if you have a centralized botnet structure, it might look something like this. So a centralized server is sitting here, and all of these are slaves: S1, S2, S3, S4, S5, S6, all these are slaves. And the instruction what need to be done is told by this server. An administrator, the bot master, sitting here, initiate by maybe sitting at a command prompt, he type something, and then the action get triggered, and all of them together can start generating the topic. Maybe if you go back to the previous DDoS attack, if another server is targeted, and then they can generate the traffic to this victim server simultaneously. So under whose instruction? This admin or the bot master's instruction. So this kind of a structure is called centralized. So of course this goes with an implicit drawback. What is that? So if this server is actually down for some reason, a single point of failure is there in this case. If the server who is at the central hub of this entire infrastructure, if this server goes down, then the whole bot infrastructure may not run properly, because now they don't have nobody to receive the instruction from. So you might do some things like having a backup server and so forth. So for fault tolerance reason, that's a different story. But the centralized bot infrastructure might look something like this. So if you go for the decentralized infrastructure, so as I said, you don't have any server sitting who is in charge of disseminating the instruction to all the C programs. the administrator or the board master actually pushes the instruction to one of the computer, maybe S1 here, and then they are connected in some fashion. So from S1 to S1 can send that instruction, pass on that information or instruction to S2 and S4, and S4 to S5, and S2 can send it to S3 and so forth, depending upon the connectivity. It might take a while to disseminate this instruction or the whatever the command is coming from the admin, because it has to go reach to all the slaves, and then only they can doing the activity. But nevertheless, if the connectivity is dense, so if the number of hops it has to, the information has to cross is less, then in short span of time, it's actually all of the slaves can actually receive that instruction. Then they can start doing the damage or whatever the things the malware is supposed to do. So this is the decentralized. This is also called as I said, peer-to-peer